Hello everyone. I'd like to begin this unit on hydrological e-flows methods by presenting the Tennant Method. This is perhaps the oldest and best known of the methods that include ecological considerations and that can be used to recommend flows to meet multiple objectives. In a 2003 review of e-flows methods used around the world, Rebecca Tharm reported that the method, or some form of it, was the most widely applied of the hydrological methods. If we consider any approach to e-flows recommendations based on a percentage of average annual flow to be somehow linked to the Tennant method, then it certainly remains the most widely used method today. But I feel it should be clear at the beginning of this lecture that while there's much to be learned from examining the Tennant method in this course, it's not representative of best practice in e-flows methodologies today, and I do not advise using it. But given that it's still used around the world, it's important that you're aware of it, that you understand its place in the developmental history of e-flows, and that you understand its limitations and why it's no longer best practice. The method was published by Donald Tennant in 1975 as a report of the U.S. Fish and Wildlife Service, and again in 1976 as an article in the professional journal Fisheries. He labeled it the Montana Method, but because of his strong personal link to it, over the years, it's come to be known as the Tennant Method. As you read the 1975 report in this unit, the personality of the man will clearly come through. He was passionate about the topic, as shown by the quotes on this slide. These are the first and the last sentences of his report. There were actually two very distinct methodologies presented by Tennant in his 1975 report and 76 paper. The first is a holistic method used by the U.S. Fish and Wildlife Service during these years to recommend e-flows for more than 100 river reaches downstream of dams across the USA. The second is the hydrology method that has become the Tennant method. The hydrology method is derived from the results of the holistic method as an index for expected aquatic condition based on a percentage of the average annual flow recommended as an e-flow. These distinctions will become clear as we go along. First, it seems that both the holistic method and the hydrology method begin with determining the average annual flow of the stream or river at the location or locations of interest. Tennant directs the reader to hydrological data of the U.S. Geological Survey. Tennant makes several references to the importance of USGS data, and he also relies on the established credibility of this organization to add credibility to the resulting e-flows recommendations. The decision to use average flow is somewhat unexpected because hydrologists generally advise using median flow or other percentiles of flow, which are considered to better reflect true conditions in the river or stream. It's not completely clear in the method why average was chosen, but it appears to be mainly due to the simplicity of calculating the average and its ready availability from hydrological data sets compared to percentiles or other statistical values at the time. Tennant also writes, citing a 1974 USGS study, that average flow can be accurately estimated by simple measures of channel geometry. Thus, he suggests that even in the absence of available hydrological data, the method can be applied. This slide includes photographs of 6 of the 11 rivers studied intensively in the testing of the Montana method. These photos were all taken near the study locations. Photographic evidence features prominently in the holistic method. These photos, including rivers from 3 different states, illustrate the basic similarity in size and characteristics of the rivers tested. This will become relevant when we look at the suitability of the method for application more widely. The next steps are specific to the holistic method. First is to visit the stream or river to observe, photograph, sample, and study the flow regimes approximating 10, 30, and 60% of the average flow. Tennant calls this photographic regression analysis. I've included 3 photos of the Mara River at different flow levels to illustrate the effect. Tennant recommends recording appropriate vital information on all photographs. Next, cross-sectional data should be obtained or directly measured to determine the average width, depth, and velocity related to the flows of 10, 30, and 60% of the average annual flow. This information is then used to check that the values meet the known requirements for aquatic resources in the river. From the available hydrological data, the patterns in average daily stream flow regime and previous historic low flow data should be analyzed to determine the base flow patterns over the course of a year. Flow recommendations should reflect these patterns. Tennant generally recommends consideration of 2 seasons, but acknowledges that conditions in some rivers may require more seasons to be considered. And the final step, based on everything learned in the previous steps, is to recommend the most appropriate and reasonable flows that can be justified to provide protection and habitat for all aquatic resources. Although only briefly described, these steps are clearly intended to produce custom flow recommendations for a given river reach based on detailed hydrology, hydraulic, and ecological studies, including field studies. Although not mentioned, we know from the content of eFlows assessments produced by the U.S. Fish and Wildlife Service that recreational values were also studied, including their economic aspects. This table is also presented in the method section of the report and has become synonymous with the Tennant Method. Donald Tennant actually encourages this by writing, quote, "The Montana method is so brief it can be typed on a 3x5-inch card. It can be applied rapidly to many segments of thousands of streams by referring to Table 1 of this paper and surface water records of the U.S. Geological Survey." End of quote. The exact logic and steps to produce this table are not described in the report, but it appears to be a simplification of the main elements of the holistic method, including an indexing of the observed conditions of the assessed river and percent of average annual flow recommended over 2 seasons, which we know was Tennant's preferred seasonal approach. Let's break down the information in this table to see what more we can learn about the method and Tennant's intentions. To begin, it's clear that the method considers multiple objectives, including flows required for fish, wildlife, recreation, and related environmental resources. These related environmental resources are those necessary to the welfare of the named objectives, and include insects, mollusks, riparian vegetation, etc. We saw this multi-objective approach reflected in the last point of the method narrative as well, which calls for eFlow's recommendations to provide protection and habitat for all aquatic resources. Next, the method clearly distinguishes between different levels of general condition of fish, wildlife, recreation, and those related environmental resources. This represents a further refinement of the overall objectives. Maintaining optimal or outstanding condition of fish, wildlife, and those resources would likely be the objective for important biodiversity or conservation areas, while good to excellent conditions may be more of a baseline objective to be applied everywhere else. Fair to degrading conditions would likely be considered only in already degraded systems with little chance of restoration. These 7 levels of condition are more than were explicitly identified in the holistic method, so Tennant must have felt that the results obtained from the many holistic studies were sufficiently abundant and consistent to justify this level of detail. As mentioned previously, a core aspect of the method is the use of percentages of average annual flow. Hydrologists found this problematic from the beginning, and I'll provide an example later of its limitations. But it's remained a popular part of the methodology among practitioners because average is quick and easy to calculate. As I also mentioned earlier, the method distinguishes between seasons, recognizing the need for different flow levels in different seasons. Tennant chooses to demarcate only 2 6-month periods, beginning the lower flow period in October and transitioning to the higher flow period in April. These periods are chosen to align with the water year defined by the U.S. Geological Survey, which runs from October 1st until September 30th. The water year doesn't align with the calendar year because a significant amount of the precipitation that falls beginning in October is stored over the winter as snow and does not contribute to river flows until the snow melts the following March or April. In the river systems where the method was developed, many ecological processes are also aligned with this schedule. The choice and dates of these seasons has been criticized by some, But Tennant was clear in the text that users of the method can adjust the number and dates of these time boundaries as needed to align with the seasonal dynamics and boundaries of their rivers. Finally, the method recognizes the need for short-term flushing flows in addition to base flows. This is wise and foreshadows more recent methods that include floods as essential parts of an e-flows regime. But Tennant treated his flood recommendations cautiously. He recommended a value of only 200% of the average flow, which he estimated is good for moving sediment and also good for whitewater rafting. He advised against higher releases because he assumed the released water would be clear water coming from a reservoir, and he feared this could cause severe bank erosion and damage the downstream aquatic environment if flood levels were more than twice the average flow. This is a good moment to mention that all recommendations in the Tennant method assume that the river is regulated by an upstream dam and reservoir. This has consequences for the range of water management settings in which it can be applied. A common misunderstanding that I also shared is that the Tennant method was developed based on the data in the report, but these data were intended to validate the method, which was developed based on the more than 100 holistic studies conducted over earlier years. The analysis of the validation data is not very systematic, but Tennant makes a point of emphasizing how it supports his selection of thresholds between condition levels. From very early on, Tennant is convinced that the thresholds of 10, 30, and 60% of average annual flow are meaningful in distinguishing overall river condition in rivers of all sizes and settings. He seems to have arrived at this conclusion through a mixture of professional judgment and pragmatic thinking. The 10, 30, and 60% thresholds already appeared in an earlier 1972 version of the method. When asked how he arrived at those values, at that time Tennant replied, quote, "I arrived at them just from a lot of experience looking at different flows and what I felt were good flows." End of quote. In the 1975 version of the method, Tennant also states that the flows of 10, 30, and 60% of average annual flow will, quote, "cover a flow regime from about the minimum to near the maximum that can normally be justified and recommended to protect the natural environment on most streams." End of quote. This is an example of the pragmatic thinking that went into the method, and much more of this is evident throughout the method text. Tennant knows from experience that it's very difficult to see these recommendations implemented. The three curves in this figure present average results from 1,600 different measurements of velocity, depth, and percent of substrate covered with water, all on the y-axis, plotted against percent of average flow on the x-axis. These measurements were made as part of the effort to test the methodology. No indication is given of the range in these values, but meeting the condition objectives of the method, good, excellent, etc., is also not presented as strongly dependent on the precision of these relationships. Tennant mentions in the discussion of these results that, quote, "In all 11 field tests of the Montana method, water depth appeared adequate for aquatic organisms whenever velocities were satisfactory." Perhaps the most important use of the hydraulic data is to support the lower threshold of 10% of average annual flow. Tennant states that the values of depth and velocity at the 10% threshold mark the lower boundary of conditions needed for the well-being of many aquatic organisms, and particularly fish. He then notes that the increases in wetted substrate, depth, and velocity between 30% and 100% of average flows are within good to optimum ranges for aquatic organisms, but without explaining the rationale for divisions between these. Specific references are not provided to justify these conclusions, but he loosely refers to there being a large number of supportive studies by government biologists and hydrologists across many rivers. A presentation of this hydraulic habitat basis for the percent of average flow threshold does strengthen the validity of the method for application in rivers similar to those used in the method development. And I expect he felt it necessary to include them because such hydraulic justifications for flow recommendations were becoming state-of-the-art in the eFlows community, and especially the science community, in the 1970s. But some later critics of the method latched on to the specific values of depth and velocity that were cited in this 1975 report. As an example of the sort of criticism leveled against the Tennant method, I've included in the additional reading for this unit a simple and recent comparative analysis made by Robert Milhous. He applied the Montana method to two rivers, one which is similar in size to those used to test the method in the 1970s, and one small Colorado mountain stream, North Crestone Creek, which is only a fraction of the size of the larger river. Milhous interpreted the depths and velocities plotted in the graph on the last slide to represent hydraulic criteria in the Tennant method for condition thresholds irrespective of river size. Not surprisingly, in order to meet these criteria in the small stream, flows much higher than 10, 30, and 60% of the stream's average annual flow are required. Milhous concluded that this reveals a flaw in the method that could be corrected by adding a river size parameter in the presumed hydraulic criteria. Now, I suspect that Tennant would disagree and clarify for us that average depths and velocities from the test he conducted of the Montana method were not intended to be hydraulic criteria to be applied to all rivers. They were measurements made to test the validity of the method as applied to the test rivers, which were all larger and relatively similar in size, as I showed in the photographs on slide 2. But a considerable amount of valid criticism has been leveled against the method. Some appeared shortly after publication of the method and was based on deficiencies encountered in its implementation, while others came later as eFlow science and practice evolved. The deficiency of using average flow was one of the first to appear when in the late 1970s, Donald Orth and Eugene Mogan of Oklahoma State University attempted to apply the method to the highly seasonal streams of the state of Oklahoma. They compared the percentage recommendations of the Tennant method to actual flows in the state's rivers based on percentiles representing the flow available 10, 50, and 90% of the time. They found that during the driest 6 months of the year, from July to December, only 10% of the average annual flow could be expected naturally more than 50% of the time. Higher percentages, reaching into good as defined in the method, simply did not exist even under natural conditions. This is the danger of the average, which can be highly skewed by short-term floods during rainy months. They also found that even during the wetter months from January to June, only 30% of the average annual flow could be expected in the river more than 50% of the time. Thus, they arrived at eFlow's recommendations of 10% of average during the dry season and 30% of average during the wet season for the state's rivers. This corresponds to the condition of fair or degrading in the Tennant method. It was clearly not their objective to recommend this condition, but they could not recommend higher values because they simply did not exist naturally during the majority of the season. In the end, they effectively recommended flows equivalent to slightly more than the 50th percentile rather than an intentional percent of annual flow, average annual flow. As a result, they recommended that use of the Tennant method should be, quote, restricted to initial planning, end of quote, and that it be followed up by intensive field analysis, which essentially means that the original holistic method should be used and not the simplified index to average, which was made by Tennant. This paper is in the additional reading folder of the unit, so you can review it yourself. They also note that the recommendation of single base flows for 6-month periods is, quote, inadequate to closely simulate the natural stream flow regime or to provide flushing flows, end of quote. And they note that flows could be recommended on a quarterly basis instead. No recommendations are made for flood or flushing flows, which are obviously a significant feature of the river flow regimes of Oklahoma. In general, Orth and Mogan choose their words carefully and do not criticize the Tennant method outright. This is somewhat surprising given their results, but then Donald Tennant was a reviewer of the paper. Criticisms leveled against the Tennant method over more recent years have also emphasized its oversimplistic representation of the natural baseflow regime of rivers, its exclusion of more dynamic flood regimes, and its unsuitability for application to rivers in differing physiographic settings and climate regimes. These are mostly all valid criticisms. There's little justification for the overconfidence Tennant had in the universality of the method. He did, after all, write that, quote, "There is significant hydrological and biological evidence that the Montana method can also be used successfully on streams throughout the world," end of quote. I don't, however, fault Tennant for his efforts to make his recommendations as simple and implementable as possible. Remember that he was a pragmatist with considerable experience in the difficulty of seeing EFLO's recommendations implemented by dam operators. The information on this slide was gathered in 1970, comparing the minimum flow for fish recognized by operators of 23 dams to the recommendations made for these same dams by the U.S. Fish and Wildlife Service using the holistic Montana method. In only one instance was the Fish and Wildlife Service recommendation adopted, and that required 10 years for the U.S. Congress to reauthorize the project. In most of these cases, the U.S. government is both the dam operator, as the Bureau of Reclamation, and the source of the EFLO's recommendations, as the Fish and Wildlife Service. One would think that being part of the same government would offer the best opportunity for aligning operation with best practical holistic recommendations of the day, but no. This recognition motivates many of the practical aspects built into the Tennant method. In the end, however, we can conclude that Tennant's attempt to synthesize the results of more than 100 custom holistic EFLO studies into an index fitting on a 3 by 5 inch card and relating only to the average annual flow of any river was valiant but unsuccessful in the end. All right, time for the take-home messages for this lecture. First, the Tennant method attempted to synthesize the results of more than 100 holistic EFLO studies into an index methodology that could be applied quickly and easily using only the average annual flow of a river. The approach sought to meet multiple objectives of EFLOs for fish, wildlife, recreation, and related environmental resources for different levels of river condition across different seasons. Now, the original holistic studies were likely valid, but Tennant's attempt to reduce their results to a simple index has proven to be flawed in significant ways. It is not recommended for use today. Fortunately, a number of newer and more valid methods have been developed. We'll turn our attention to those now and in the coming units. That's the end of this lecture. Thank you.